So, like I was saying, RE prime. So when we use DC, the RE, we're going to call it RE. It's going to be uppercase, right? You understand? RE prime is the dynamic resistance of a p-n junction. So we know from our diode lab and setting up that characteristic curve that when I forward bias a p-n junction, it is not a straight line, right? So what it does is it actually comes up and gives us a slant, right? Looks like I closed out my PowerPoint. So the diode, a p-n junction, when it's forward biased, then it comes up here and it comes up and then it comes up and it goes up at an angle. Now, because why? Because now we're dealing with the resistance of the semiconductor. So a guy, he came up with the equation so we can use to calculate this. And this is the dynamic resistance of a p-n junction, which basically, let me get the right one up here. Where's it at? Let's do this. Which is going to deal with a little calculus, but this is the formula that they came up with. And they come all the way down through here and solve all this. Of course, one thing we have to deal with Kelvin. You know what Kelvin is? What's Kelvin? 0 in Kelvin is where all molecular motion is supposed to stop. So that's freezing. So that's where 0 degree Kelvin is. It's based on the spacing of the centigrade scale. So 273 degrees Kelvin would be 0 degrees centigrade. But the spacing between the degrees is the same as the centigrade scale. We have what they call Rankine. It's where absolute 0 in Rankine is based on the spacing of the Fahrenheit scale. But you see, in electronics, we basically use centigrade. So, and then you have to know the charge of electrons is approximately Boltzmann constant, which I have no idea what that is. The exponential constant, approximately that. And you plug all of these in the formula, and you go back down through here. You go down through here, and here what are they using for temperature? Probably 25 degrees centigrade. And then they come up with this guy right here. So RE prime, and it says equal, but that's only going to be equal exactly that at an exact temperature, right? You understand that? But this is what we're going to use for approximation. So R shouldn't say equals, it should be approximately 25 millivolts over IE. Now IE is your bias current. Because AC, even RE prime changes, it's going to be averaged down the center, right? You understand that? So 25 millivolts over IE, that's the way we can calculate the dynamic resistance of a p-n junction. Are you okay? Yes or no? So what we do to calculate the gain now is we take our same equation that we used before, this guy right here, and instead of using RE, I'm going to use RE prime. So let's calculate IE. So we did it a while ago. So let's do the actual measurements here. What do we calculate here? So I can't erase that. What was our actual calculations? So what did we calculate VB to be? What's that? 1.8 volts. Okay. And then we calculated RE to be what? Or do we need to recalculate that? Y'all remember? 1.1 volt. Okay, but we calculated this to be what? Now we have this back up to 20 volts the other night. So let's go recalculate. Let me make sure. Huh? At 20 volts. Yeah, but remember last time I had like 16 volts and I didn't want to rewire it to get to 20 volts, but I have it now. So 1.8 volts, then we got what? This would be 1.1 volt, and so that means I'd have 1.1 milliamp, right? No, we're not concerned with that. We're calculating RE prime. We're through. All we need to calculate RE prime. So RE prime is equal to 25 millivolts over IE, which would be 1.1 milli. So what's RE prime? A milli's going to cancel out, right? We got it on the top and the bottom. So it's going to be 23 ohms or something like that, 22 ohms. $22.7. So the way so if you look at your formula for AV, it says two things. It says R out, and then out the bottom it's got RE, and hopefully it's got this, or RE prime. So what you're going to do is you're going to select one. If it's bypassed, we're going to use what? We're going to use RE prime. If it's not bypassed, we're going to use what? RE. Y'all understand that? So what I'm going to do is I'm going to say, what was our R out? What was our R out? 9.1K. Okay, I'm going to divide that by RE prime. Was RE prime 22.7? What gain should we expect? Now this is truly a guesstimation. What do we expect? 9.1. Y'all remember that? I'm sorry. 9.1K. It was 9.1K. I didn't write the K up there. I can't cancel that. 9.1K divided by 22.7. So we should expect a gain of about what? Huh? 400? Is that right, guys? This is a 10K. That's a 100K. It came up to be 9.1K, right? 400? Well, we'll see. So let's see what we got. Now, this is definitely an approximation because what we're dealing with is we're dealing with the dynamic resistance of a PN junction, right? You understand that. So let's see what we got. So I'm putting, what did we calculate a while ago? So I've got 40 millivolts in, and I've got what out? 2 volts out. So what do we actually measure? Well, let me check. Let's check the voltages first. Wait a second before I get all puzzled. Make sure I got 20 volts on there. So this is calculated 20 volts. So my power supply voltage is sitting at 18 volts. So it's off a hair, not much. And my base voltage, my emitter voltage is sitting at 1 volt. So that's about right, isn't it? Yeah, we're getting about half the gain in what we expected, which is still not bad for all the approximations we're using. So this is the scope. So this we have 200 millivolts per division. Can y'all see the divisions up there? Let's see. So we have them on 20 millivolts per division. How many divisions? Two. So it's 40 millivolts. Millivolts per division. 2468. So that's that's exactly 400. I'm sorry, that's 200. Right. 400 millivolts in. 400 millivolts in. It goes out. That's 200. So we got a gain of 200. We calculated what? 400. But what you have to understand, when we start dealing with RE prime, then we're probably going to calculate a lot more gain than we actually got. Okay. Yay, nay. Ain't that neat though? Here, I'm going to take the capacitor out. See what the output did. Now we're still getting gain, but now we're back to a gain of 10. I put the capacitor in there. Now the problem we have, why don't we bypass everything? Well, the problem we have is this. Sorry, guys. Still not the right one. Yeah. So I'm going to go ahead and get rid of all this stuff, and I'm going to redraw the circuit so we can get a good look at this and tell you why we don't bypass everything. And then later on, next class, we'll talk a little bit about something called impedance matching. Don't let me forget that. Why is it doing that? I'll be with y'all in a minute, guys. This is a 100K, right? This is a 10K. This is a 10K, and this is a 1K. Now, what we're doing is we're bringing a signal source in here This is not a power source. This is a signal source. Now, there's no such thing as something that does not have any resistance at all. You don't understand that? If I push voltage through resistance, what do I get? I get a voltage drop, right? So this is why if I came over here and I have a battery, you go out and buy a C cell, and you come over here and you take your voltmeter and you put it across it, and then you come over here and you put a 100 ohm resistor, what's the voltage going to do? It's going to drop. Well, what's dropping it? Well, the internal resistance of the voltage of the source. So all sources basically look like this. And then, of course, what we see over here is we see the plus terminal and we see the minus terminal. Y'all understand that? Well, what we do on a regulated power supply is that we appear to make that thing right there disappear. Because what we do is if the output tries to drop down, our regulator automatically raises it back up, right? So a regulated power supply is like it'll put out whatever current it can until you get out of the range of out of the limits of regulation. Now Alabama Power has got some really good regulators down there on their alternators, and by George, if you get a short on that, we burn stuff up, right? You understand? Now a signal source, a source of a signal. So remember, we got two things. This guy here does not create power. Where does the power come from? Where does the power come from? The power comes from that power supply right there. That's why it's called a power supply. So transistors do not create power. They just control it, right? You understand? So when we say we got power gain, if I've got a 100-watt power gain, then by George, I've got to have a power supply that can provide that 100 watts. So transistors do not create power. They just control it, right? You understand? That control current. But when I hook up a signal source will always have that resistor right there. We're not talking about a power source. Signal sources are not regulated. If I tried to regulate volume, then I wouldn't get any sound, right? You understand that? So every signal source has a resistor. So that means I come over here and I draw that little AC thing, then what I need to do on every one of these is do what? Put a resistor in series with it. So how much does that resistor right there drop? Depends on the watt. V is equal to what? Okay, it's equal to I times R. So what determines, and this is AC, so we come in here with this thing right here, and here comes my AC signal, comes through that resistor, which causes some voltage drop, comes up here, goes that way, and then goes that way. So how much current is required by the input of that amplifier determines how much that drops. Okay, y'all understand this? Y'all following that? So to calculate my input resistance, we'll call it Rn. This would be equal to 1 over 100K plus 1 over 10K plus 1 over Re times beta. Now remember, from the input point of view, the input sees that resistor as times beta. And what law is this? This is your parallel circuit formula. All we got to do is just remember to mark that times beta. So right now, typical beta for a 3904 is 100. So we'll just use that because we're trying to get an approximation anyway. So Rn would be equal to what? 1 over 1 plus 1 over 10K plus 1 over 1 plus 1 over 100K. So what I did in my head is I took R, which is this, and multiplied beta And what's my internal resistance now? What does my source see? So somebody work that out for me. Shouldn't take very long, guys. Y'all should have done all these in DC, right? So it'd be 100 times 10 to the third reciprocal plus 10 times 10 to the third reciprocal plus 100 again times 10 to the third reciprocal equals reciprocal. So I've got 8,333.33 ohms, or a little around 8K. We okay? And we knew it's got to be smaller than this guy right here, but you got these 200Ks in there. Okay. Now if I come over here and bypass that thing, what did we just lose? We lost RE. Okay. So what we got now is we got this. We got Rn equals to 1 over 100K plus 1 over 10K plus 1 over beta times Re prime. So now Rn would be equal to 1 over 100K, it's supposed to be K, guys, plus 1 over 10K plus what? Re prime is equal to 23 ohms times 100. That's going to be 1 over 220 ohms, or close to that. So what's Rn going to do? Is it going to go up or is it going to go down? It's going to go down a lot, right? So that would be 100 times 10 to the third reciprocal plus 10 times 10 to the third reciprocal plus 220, or around there, reciprocal equals reciprocal. So now my input resistance dropped down. This guy is setting the input resistance now. So Rn dropped down to what? About 215 ohms. So it means now my signal source is going to be loaded a lot more. So now my signal voltage is going to drop down because my input requires more current, right? You understand? Y'all understand that? So the advantage of not bypassing is we get a higher input resistance. We get a lower gain, but we get a higher input resistance. The advantage of bypassing is we get a higher gain, but we decrease the input resistance of the amplifier, which means now my signal source, so I'm coming off my antenna on my car. You think the first amplifier we're going to run that antenna into is going to be bypassed? Yes or no? Well, no, that antenna's got at least 300-400 ohms worth of resistance in it, right? You understand? We usually have about a 300 ohm antenna out there. So that means, by George, it wouldn't even be able to drive the thing to get the gain, right? You understand? Because it would drop all the watt. It would drop all the voltage. So what we're going to do, our first stage is going to be not bypassed. So that way we can get voltage gain and we can get current gain. Now my second stage can be what? Bypass, because now we got this guy that we get all this voltage and current gain out of, and we can feed that into, we actually feed it into what we call a swamp. I'll show that later. So what we'll do is we'll bypass a part of RE, and then toward the end we're going to bypass all of it. So normally we go through 2 or 3 stages of application. The first one, we're looking for a high input resistance, right? So it won't load the watt. It won't load the signal source. In fact, later on, we'll see that normally we use an FET there. So normally your first amplifier will be an FET amplifier because it has extremely high watt input resistance. But you can see why when you look at the schematics on stereo amplifiers, they go through what? They go through stages. First, we want a little bit of gain, but we want a high input resistance. Then we're going to start dropping the input resistance down, right, to understand, because we're going to get gain out of these transistors. So 3, 4, 5 stages of amplification. I can show you all this transistor rate. Now, of course, now when you work on radios, your whole amplifier is still going to be in one IC. But your power amp is still going to use, on a big, nice power amp, it's still going to be transistors. And I'll show y'all one we got there. We got some schematics on some power amps. So power amps still use a lot of discrete components because it's hard to integrate 250 watts into a little integrated package, right? You understand? But your preamps are going to be probably modular now. So if you tore your radio apart in your car, you probably got one big nice IC in there doing everything. Well, you probably got two. You got one that's the preamp, and then you probably got one that's got the power amp. But it's probably going to be an integrated circuit. That's just what I came up top of my head. RE prime. What was that? What did we come up with RE prime? What was our RE prime? 22 point something, wasn't it? Well, we multiplied that times beta. So I did that wrong. 22 times beta. So 22 times beta, I did it by 2, so it would actually be 2,000. It would actually be 2.2K. Thank you. But still, it's going to drive the input down. So over here, we were sitting pretty close to that. Over here, we're going to be sitting pretty close to the 2.2K. So I calculated wrong. Thank you. So where did the 220 go? I multiplied times 2.2 in my head instead of 22. So what would the gain be? I mean, I'm sorry, what would REN be? It would be 100K reciprocal, 100 times 10 to the third reciprocal plus 10 times 10 to the third reciprocal plus 2200. Reciprocal equals reciprocal. So we're at 1.8K. Still, we're going from 8K to 1.8K. So the advantage of not bypassing is you get a higher input resistance, right? The advantage of a bypass is we get higher gain. But you don't get something, you never get anything for nothing, right? So what you're going to notice is that we sacrifice one thing to get one thing. So we call this, what do we call this guy here? It's called a bypass capacitor. Well, these two guys call right here coupling capacitor. You need another name still. And the circuits are fairly simple to hook up. I'll leave this a bit up so when it comes time for y'all to start hooking these amplifiers up. And basically, this is the last lecture on bipolar transistors, or a common emitter. What we'll do was look at the common. We'll look at a common base, but you're probably never going to run into a common base because all you get out of a common emitter. So the characteristics of a common emitter has a fairly low input resistance and a fairly high output resistance. The input and the output, what's the phase relationship between the input and the output? (180 degrees out of phase). So the output's 180 degrees out of phase because we're taking it across the transistor. So as the input, as the signal drives the input voltage high coming up, then the transistor voltage drop is going to go down, right? So it's 180 degrees out of phase. What are the characteristics? And that's important to know. Fairly low input resistance, which means your signal is going to have to drive a lot later on. Fairly high output impedance, which means, or resistance, which means we can't drive a lot of current. We got to have that guy right there. So this is the output. This is the output resistance of the amplifier. This guy right here. So that means the lower the load we have right here, the lower the resistor. This guy right here is going to drop more, and the gain of the amplifier is going to have to do what? It's going to have to go down. So that's one of the characteristics of common emitter. So when it gets time to when it gets time to that in that power amp, when it gets time to drive those speakers, we are not going to use a common emitter because of this high output resistance right there, or high output impedance. but we can use this guy to get ready to give us the drive. Does that make sense? So usually we get a lot of gain out of it. You get both a voltage and a current gain. If it's designed correctly, out of a common emitter, you get both voltage gain and you get both current gain, which means we can get quite a bit of power gain out of this thing, right? Because power is equal to what? B times I. So that's one big advantage of a common emitter. You'll get both a what? If it's designed correctly. Not if you just go out and just throw stuff in there. If it's designed correctly, you get a watt, you can get a what? Current gain and a voltage gain. All right? So characteristics. Input resistance. Power low. Low. Output resistance. High. Phase relationship. Right? The gains we can get out of this thing. Of course, all of them give us a power gain. Y'all understand? So when we ask for the gain of an amplifier, power would be is not is on all of them, right? You understand? So when I talk about the gain of an amplifier, I'm talking about what gain do we get to get the watt power gain. So what two gains do we get out of this guy? We get a voltage gain and a current gain, and that's the characteristics of common emitter. Are we okay? All right, guys. Y'all take a break, and then we'll come back and go to the lab. I got to find one more transistor for y'all. So we're not through with bipolar transistors. We're through with the common emitter. And we have a worksheet to do during the weekend. And I'll have to send